Okay, we have here today another interesting integral from the MIT Integration Bee from 2015, number 6. We have the integral from 0 to e x ln x squared dx. Okay, whenever we have ln x, the thing I'm usually thinking about is either integration by parts or u substitution or both. In this case, I prefer to use a u substitution first just to kind of clean it up a little bit. So for my u, we'll just make it this thing. We'll say u equal to ln x. I want to isolate x before taking the derivative. So with this, I can just rearrange this and get this as x equal to e to the u. Then we can take our derivative here. The derivative, we'll get dx on the left. This is going to become derivative eu is just eu du. Now from here, let's plug this all in and update the bounds. So when I plug in here, ln of e, that's just 1. Then plugging in 0, ln of 0, that's going to be going to minus infinity here for our lower bound. Then for x, we've got our value. We have e to the u here. This is going to become just u squared. Dx is going to be eu du. But then notice we get really the same thing here. We get the same base, actually eu times eu. We multiply these together. What I can do is combine these and make this a 2u right here. And then we can just get rid of this other one. But now that we have an expression with two different components here, what I want to do is integration by parts. We'll do the DI method or tabular integration over here to the right. Let's just set up our tables. So we're going to have one column to differentiate, one column to integrate. I want to differentiate u squared because that's going to reduce. So we'll do this one over here and we're going to integrate e to the 2u. And we're going to need to do it a few times. So let's just make, how many times? It's going to be 4 times, I think. So let's just do this. So I'll differentiate u squared and we're going to get 2u here. Derivative again is going to be 2. Derivative again, derivative of 2 is just 0. Then integrating down this right column here, integral of e2u, we're going to get just e2u, but we need to pull out this 2 in the denominator. We do it again, we get e2u over 2 times 2, or 4. And then for the last one, we have e2u over 8. We don't have to worry about integrating our last row because we have a 0 here. It's going to 0 out that integral. So we can just take our solution on the diagonals. We're just going to have 3 terms here. And notice we have e to the 2u in common in each of these. So when I rewrite this, what I'll do is let's just factor that outside of the expression. So I'll bring this in front. We're going to have an e2u and everything. And then we need all this stuff. So this is going to be, but we also have this like half, fourth, eighth. So for like this first one, I can write it as u squared over 2. We have a minus sign here. I can write this as minus 2u over 4, but let's reduce that to u over 2. And then here we're going to have just 2 over 8, I'll reduce that to a positive 1/4. And then we just need to evaluate from minus infinity to 1. So now let's just plug in 1 to start. So we plug in 1 here, we're going to have, this is going to become e squared. Here we're going to have 1/2 minus 1/2. And then here it's just going to be plus 1/4. And that's that part. Now for the minus infinity, when you evaluate e to the 2u times minus infinity, that's going to be like e to the minus infinity. So that piece is going to be going off to 0. You have all this other stuff, but then what's going to happen here if you take a limit, the exponential is going to be much more powerful and it's going to overwhelm all this other stuff. So this is just going to be a 0. Then with a quick simplification here, half minus a half, that's a 0. So that's going away. We're just multiplying e squared times a 4. So for my final solution, we just have e squared over 4. Okay, there you have it. Good integral from MIT 2015. Thanks everyone for watching. Have a good day.